You are listening to EE Times On Air, and this is EE Times Current. For Eric Singer, I'm Taylor Marvin. Welcome to Brains and Machines, a deep dive into neuromorphic engineering and biologically inspired technology. In this episode, you'll hear from Dr. Shih-Chii Liu of the Institute of Neuroinformatics in Zurich. Your hosts are Dr. Sunny Bains of University College London and Dr. Giulia D'Angelo of Fortiss in Munich.
Welcome to Brains and Machines. I am Giulia D'Angelo.
And I'm Sunny Bains.
In today's episode, Sunny is talking with Dr. Shih-Chii Liu, co-director of the Sensors Group at the Institute of Neuroinformatics, INI, part of both the ETH and the University of Zurich, Switzerland. After the interview, we will be talking to Rolf Etienne-Cummings from Johns Hopkins University about the issues raised.
Thanks, Giulia. Shih-Chii is a researcher with more than 3 decades in neuromorphic engineering and who has helped build the field through her direct research and teaching, but also through her helping to lead community building projects like the Telluride and Capocaccia workshops. In this interview, you'll hear her talk about neuromorphic cochlea, sparsity in deep networks, and what it will take for the technology to solve real problems in industry. There are links to her work and some of the specific papers we'll be discussing on our website. You can check them out at brainsandmachines.net. I met Shih-Chii at her lab in Zurich. Shih-Chii Liu, welcome to Brains and Machines. Let's start by your telling me a little bit about your technical background and how you got involved with neuromorphic engineering.
I studied electrical engineering for my bachelor's and my master's, and then I went to work in Silicon Valley in a company that was developing memory circuits, like ROMs and RAMs, read-only memory and read-access memory devices. And then I met Christoph Koch, actually, in one of the companies that I worked at, and I found the work that he was doing at the time in this neuromorphic engineering area very interesting. And so subsequently, I applied to Caltech to work in Carver Mead's group. And so he's the father of neuromorphic engineering. And that's when I started this whole field of my study in this area and also of research.
So what was your first project that you did at Caltech?
So for my PhD, my doctoral work, I actually built motion processing circuits that model what could be going on in the motion system of the housefly. And housefly is known for being very efficient in how it uses power. It burns only about 10 microwatts. And so we thought this was a great system to study and to look at to see how you can build such circuits also in CMOS technology. And then from then on, I went to different workshops like the Telluride Neuromorphic Workshop. At the time, there was only one neuromorphic workshop, and I ran into Andre Van Schaik, who was building silicon cochlea circuits, and then we decided we would get together and start building spiking silicon cochlea circuits, and that's how I got into now this auditory processing neuromorphic circuits I've been working on for the last 10 years.
So yeah, that's probably the work that you're best known for. Would you like to tell us a little bit about these silicon cochlea and how they work?
So the silicon cochlea circuits have been designed by several students, ex-students in Carver Mead's group. And so what I've added to the circuits together with Andre Van Schaik is to build the spiking interface. So the original circuits were more about modeling the analog function in the cochlea, and to allow yet another modality besides the retina in how you would process spikes from different sensors was to use the cochlea. And once we've developed a system that would put out the spikes, then I could start looking at different models or algorithms or even bio-inspired audio circuits in the brain to see how we would actually pull out information that we could use for tasks that the commercial world cares about. For example, keyword spotting, voice activity detection. And that's what I've been developing the last few years.
Does that involve looking for or having intelligent ways to pick out features in the sounds? that you're
Yes.
receiving? And how do you do that? Can you talk a little bit about that process?
Yeah. So normally the way that people process audio algorithms in the conventional way is that you take the output of the microphone and then you sample the amplitude of the sound coming in, and then you apply this established signal processing methods for extracting the power in different frequencies of the sound coming in so that you can say something about that type of sound. In the brain, it's done differently. So looking at how brains do it is by taking the sound coming in, it does decompose it into different frequency bands, but the information is then transferred up to the brain in the form of asynchronous binary events, also called spikes. And so we wanted to see how you could extract the same kind of information in this asynchronous representation and to make sense of what's going on, and to see if these circuits will lead to kind of lower power, lower latency, artificial silicon circuits that you could use in the commercial world.
So the idea, as I guess is similar in vision sensors, is essentially that the part of the circuit that is creating the spikes is essentially lowering the dimensionality of the signals so that you have something compressed coming out, but something compressed with the important features of the sound encoded in it. And so part of your work has been to make sure that the information you need is in those spikes and to be able to decode that information into something usable.
That is correct, yeah. And also the information comes in the form of a representation in time rather than in the frequency space, which is what the conventional algorithms do. So it's different in that way. And so usually, for example, if you do something like sound separation, you would take that sound coming in, you transform it into the frequency space, which they also call a spectrogram. And then you do whatever processing is needed to extract, say, the speech of someone in a noisy situation. But then you have to still go back out to the time waveform so you understand the speech. But if you process everything in the time dimension, then you don't have to do any of that inversion process that you have to do for the conventional method.
Hi, listeners. After she heard the interview, Shih-Chii was concerned this might not have come out quite the way she meant, so she wanted to clarify. Shih-Chii doesn't mean to suggest that frequency information is not used at all in the brain, because the spikes from the cochlea, of course, carry information from different frequency channels. Instead, she just wanted to point out that they do also carry the temporal information. Okay, back to the interview. And so that's why you're really getting the advantage of lower power, is because you're doing away with a lot of the processing.
Exactly, yeah.
Another thing that you've been using, besides just the basic spikes that we're used to in event representations, is delta modulation. Can you tell us the difference between delta modulation and the normal kind of spikes?
So one way of generating spikes is by using an integrated fire model of the neuron to generate the spikes that go out. Another way of doing it is that you take the analog signal and you look for when the signal changes by a certain threshold. And when it changes by that amount, then you send off the spike, right? So it's another form of encoding. And what we're trying to see is whether this form of encoding makes it easier for us to extract information.
So essentially, it's taking more information from the signal. So instead of saying, yes, there's something going on, or no, there's nothing going on, it's saying, yes, and then it happened again, and it's going up again, and it's going up again. So you're really seeing a more
faithful representation of what the input is doing. Because when you see the spike, you know that the signal has changed by X amount, right? And so then you know more about the analog information in the input.
So what have been the benefits of that? Have you been able to quantify those?
Yeah, so one thing we found is that if you take the spikes that come out from that representation, you can reconstruct the original analog information. So if I take a speech sample and then I process it and produce this delta modulated spikes, then I can reconstruct the original speech so that it sounds closer to what the input was. But if I use the spikes from the integrated fire model, then it's more difficult to go back to the original speech. It's not to say that we need to go back to original speech, but it's a way of understanding whether the spikes that you're generating still has the information from the original input.
So it's a more faithful representation. It must also have some kind of overhead in terms of circuitry and maybe in terms of the bandwidth that you're using, that kind of thing. What's the trade-off there?
Actually, we don't see a difference or even an increase in the bandwidth that you have to use. In fact, I think the circuits are simpler. But it might not be similar to how the neurons in the brain are generating spikes. Right. So usually we have to do a trade-off between what we know will work well for engineered systems versus what the brain's using.
So it's more of a trade-off from the biology than a trade-off from the efficiency.
Yes, that's correct.
Another thing you've been working on over the last few years has been taking neuromorphic principles like sparsity and applying them to more conventional deep networks. Can you talk about that work and the sort of payoff of doing that?
Right. Yeah, so in the last few years, you can see that the neuromorphic world is also using ideas from the deep neural network community. For example, for training the systems so that they can work on the output of the sensors, so that you can do something that is robust and accurate. So in the audio world, it's keyword spotting or voice activity detection. And the networks usually are artificial networks that you timestamp. So you get the spike inputs from the sensors, we create frames, and then we pass it to these networks. And so they're not spiking networks, but you can train these networks easier. But we thought that these networks could also benefit by the features of a spiking neuron. So in a spiking neuron, there's usually a threshold where the neuron will produce the spike. And so we thought it would be actually useful not to communicate the output of all the neurons to the next layer, but rather we look for neurons whose change in activation or change in the output value has exceeded a threshold. And those neurons we consider as active neurons, and we only pass information from those neurons to the upper layers, which means that if I have 1,000 neurons, maybe 2 of them are considered active, and so we only have to send information from those 2 neurons to the target neurons in the next layer. Therefore, saving a lot in energy, because energy comes when you have to fetch information from memory. And when you do this, you always burn energy. And so the idea is to cut down on the energy that you need to fetch the information. And also for storing, say, the parameters of the network. So this is what we call the delta network.
Did you say this was the one that's with weight sparsity or with connection sparsity?
So this is with activation sparsity.
Activation sparsity.
Okay. Yeah. It works more like a spiking neuron in the sense that when you have a spiking network, only the spikes that are produced will be used to update neurons in the upper layers. So this is similar in the sense that only neurons whose change of activation value has crossed the threshold, a defined threshold, are allowed to send your information upwards. So it's similar in that way that not all neurons need to be updated or need to send your information. Only a subset of neurons that are active send your information.
And so what kind of proportion of activity can you reduce it by?
Usually we can cut down by more than 50%, depending, of course, on the task. And usually I work more with audio tasks and data sets. And so we found that in using these established data sets, we can save more than 50% of the neurons that need to update other neurons. So we find that was useful. Now, another form of sparsity which people in the deep network world also work on is to reduce the number of weights that you need to use in your network, because that would save on the number of parameters for the network. And usually this is called reducing the memory footprint of the network. And there you save by not storing the parameters, and therefore you're not using energy to fetch those parameters. And in those cases, we actually found most of the time you can actually train the network so that it can throw away more than 90% of its weights, and you'll still work great.
And in order to do this well, does it involve more complexity in the training? What's the overhead?
It's true. So the training is more complex because it has to take into account that you want to reduce the number of connections between the neurons. And so that means the training process will take longer for the neurons to come to an architecture where a few connections are needed and fewer neurons are needed. right? But it does seem to work well in almost all cases that we've looked at.
That's really interesting. You've been in the field since the very early years at Caltech and the subsequent birth of the Institute of Neuroinformatics here in Zurich. I wonder if you could possibly talk about the most important changes you've seen in neuromorphic engineering over the years, maybe both internal, like ideas that have come and gone, but also external and how you think the field is viewed by the outside.
It's a very good question. And I also find it very interesting to look back and see how the field has evolved. I think when I first went into the field, it was more based on biology, right? So the idea was to understand the structure of the system and to build it so that you understand something about the function, right? And the retina is a great example, and also the cochlea. But what's probably, I don't want to say difficult, but challenging is that we also would like to show that the systems that we build are also useful for industry, which means that we have to trade off some of the circuits or ideas so that it encompasses also some part of what the traditional fields have discovered or developed, for example, in signal processing or in computer science and so on. And so as a result, I think what has happened to the players in the field is that they don't just include engineers, circuit designers, and biologists, but they also include now computer scientists, robotics, people who work on control from the more conventional ways. And I actually find this very useful, and I think it also makes the field develop much better because many of these ideas can be combined together to make an engineered system that works closer to that of the brain, but also has a lot of features or qualities that will make this system more robust when it's constructed. Because the system that we build are built out of transistors, of CMOS circuits, and they're not built out of biological material that's in the brain. So we can't just copy what the brain has, right? It's not possible. So as a result, we should use the best of what the silicon world can do, what the digital world can do, and also what biology can do. I think we're going to come to the best solution. In fact, this is also what's happening in the different groups around the world that have adopted neuromorphic engineering, that it's no longer like the neuromorphic engineering research of the old days, but rather you'll see it's a combination of different techniques from different fields together with something about biology. A lot of times it's using the principles of what the brain uses and then applying or adapting it to the kind of technology that you have.
And what about the external perception of the field?
So because this field or this terminology has been adopted by many, many more groups in the world, I think they actually find it attractive because it's not just the conventional engineering solution, but really looking towards the brain to see what principles it could be using to make it low power and to make it intelligent. And because the original solutions require systems that use more power, we know that's not probably the architecture that's being used by the brain. And so one example is that instead of using the von Neumann architecture of the computer, we've now moved toward a more distributed architecture where the memory and the processing are co-localized together. And this is what the brain uses because the synapses store the local memory and then the computing is done within the neuron. And in the deep network world, this is definitely happening, at least in the computer architectures that are being produced. And now also in the technology where people are developing memoristic devices and talking about in-memory computing architectures. So this has the elements of the distributed architecture that the brain's using. And so that's why now these neuromorphic features are also adopted by people in the conventional world when they're building the next computing architecture.
It's interesting to me, when I was at Capocaccia, right before I arrived there, Jeff Hinton had made his pronouncement on leaving Google that AI was dangerous, and Jan LeCun said the opposite, that we're nowhere close. But what's interesting to me is these are both people who I'd met loosely through the neuromorphic community decades ago, and who might have been considered part of that community. So actually, some of the strides forward, like deep learning, they actually kind of come out of neuromorphic engineering in a way. Would you agree with that?
Yes, I think the researchers that you mentioned are also interested in how brains compute. They're driven by the same motivation, if you like. Maybe in a different way, they're using computer science as the tool for understanding how you could build better computing architectures, right? But they're also looking towards the brain for ideas that they could encapsulate in their work.
We're at the point where the field is expanding very rapidly. The definition of neuromorphic engineering is also expanded quite a lot, as we've discussed, but we won't go into that too much here. Yeah. Where do you think the field is going? What are the things that you think are promising and maybe a little bit negative?
So I'll comment more on the engineering side. So there's a lot of interest in looking for applications where neuromorphic engineering can shine. And we need to look at applications where the computing platform will have little memory and little compute resource. So as a result, we can tackle problems that require small networks where you would burn less energy. So we're not looking to build servers that can replace the servers that people use for computing deep networks, for doing image captioning, et cetera, and so on. And so we imagine this is where neuromorphic engineering will come up with solutions that would lead to lower latency and lower power systems than what conventional methods could give us. The other thing I want to touch is there's a lot of interest now in learning, and the brain learns in a way that's very different in how these deep networks are trained. In fact, it seems like we can learn much easier on the fly than what deep networks can do, because usually what you do is you have to retrain the whole system again on all the examples that's given, and that's extremely costly. But our brain seems to be able to learn even when it's only given a few examples. And I think learning and also the circuits that come with it are going to be something interesting that neuromorphic engineering could produce as possible solutions in the future.
So we're talking about small, lightweight systems and eventually learning systems. Yes. So the idea might be that something like the SynSense chip, which today is purely an inference chip for vision, for instance. Yes. These chips might one day be learning on the fly, learning to recognize new things.
Yeah, or new classes of objects, but without requiring a whole new retraining schedule.
And a very last question. So I've noticed, you mentioned this earlier, I've noticed that there are a lot more computer scientists in the field. Now, what's interesting about biologists and electrical engineers who used to dominate is that they come with a very physical point of view, right? It's all about ion channels and electrons and
the electrical circuits that you can build so that you can capture the same functionality. It is true.
And so what are you finding? I'm sure you have more computer scientists in your group than you did before.
Yes, that's correct.
What are you finding that they're bringing to the party, so to speak?
So when you can build a system that approximates closer to what biology has as the alternate physical system, but it's wetware, is that you need to use the system to solve a problem, right? And so that's where computer science is important, because now you have to construct a system that uses the physical devices that we've built or the physical circuits we've built so that you can solve a problem. And for sure, engineers normally don't think about that. They're very good at building circuits that have the specifications you're looking for example, in the power that it uses or in the bandwidth that it needs. But you don't usually think of the computation that you need to run on top of it. And I think this is where students who have computer science backgrounds are great at doing stuff like this. And especially nowadays with the advances in deep networks, they can use this information to construct models or systems that run on top of these devices. And that's why you're seeing more of them in the different groups, the neuromorphic groups around the world also, because you need to have both actually to get something that works well.
Shih-Chii Liu, thanks for coming on to Brains and Machines.
Thank you, Sunny, for this lovely interview session.
Thanks, Sunny. I am fascinated about the cochlea, and for more about Shih-Chii's work, please go to brainsandmachines.net. Now, we welcome back our regular commentator, Professor Ralph Etienne-Cummings from Johns Hopkins University.
Hello, guys. Good to see you again.
Hi, Ralph. So I loved this interview. And of course, I agree with lots of things that Shih-Chii said. But actually, I was interested by the fact that she worked with Christopher Cox. And I didn't know that. So I actually dived a little bit more into what they have done together. And they came out with object-based analog VLSI vision circuits in 1992, which actually is on figure ground segregation. And this blew my mind because I'm working now on figure ground segregation and using, again, the proto-object models.
Hey, Giulia, why don't you tell the listeners more about what figure ground separation is?
So is the precursor of saying that you are segmenting the scene, right? The figure ground segregation is based on the concept and is still coming from the Gestalt principles. So trying to understand what's foreground and what's background. But actually, my question is for Ralph. So right now I'm using a recurrent neural network that is again based on the proto-objects. And then I have this feedback between the border ownership cells and the grouping cells. And then I do figure ground organization thanks to this. So I have a question. Is this work with Christopher Koch like a precursor of the work that Ernest Niebuhr came out with this recurrent neural network or not? Or is there any influence there?
So I think there must be, right? Because Ernst did his postdoc, or maybe a little bit beyond the postdoc, with Christophe. By the way, his name is Christophe, not Christopher.
Thank you.
And also, if you look at the work of Laurent Ity, all of that came from that same genesis, right? That same process. So I am certain that there were a lot of discussions that happened in that room, so to speak, when they were all there together. And that's what led to the various models of segmentation, of saliency, and ultimately towards the proto-object saliency models, right? So I wouldn't be surprised at all, although I wasn't in the room, so I cannot speak directly as to who did what and when, but certainly I can imagine there's a good set of influences that came from there.
Then I have another question. Do you think that this is enough to say that our brain somehow does the figure ground organization in this way, or we need to add more to that model?
The question is always, what is this way? In a sense, if you think about what the proto-object saliency model provides, it provides a way of determining competing borders, whether that border is front or back, right? Which one is in front of which, right? So one could argue that, since that competition between different orders were done to replicate or done to explain what has been found in the recordings from monkeys, maybe that is a little bit more related to what would possibly be happening in visual cortex itself, right? The computational models are always good as an explainer, as a means of providing us a movement towards an understanding of what's going on. But I tend to always lean back on what explains the neuroscience a little bit more, because I think the neuroscience is what happens in the brain, right? Now the question is, how do you explain that by having a good mechanism for doing so? One of the things that you mentioned was that Shih-Chii was working on these figure ground separation chips, right? Or in VLSI, as you indicated. I would like to point out also a chip done by Gert Kauenbergs. That is a particular chip that he designed to exactly figure out which borders belong to which object. He had this competition between, again, a competition network on chip, and he was able to demonstrate that he could pull one object out and suppress another one based on their relative closures and the relative position in the scene. So that would be a great accompanying piece of literature to read.
And actually a future podcast, because we're going to be talking to Gert in the next season. So something to look forward to. You wanted to change the topic, Giulia.
Yeah, I wanted to say, and I think it's important to mention the fact that Shih-Chii won the Misha Maura Prize in 2020. And together with the team, which is Enea Teolini, Daniel Neal, Anu Mula, Kleslev, Brown, and Huber, which I think it's very important to tell all the people that were inside. It's a great piece of work. Then another thing that I was thinking about, so every time I think about the cochlea, I remember about Helmholtz, and when I was studying Helmholtz at a university, and he was like from 1867 suggesting to model the cochlea of the inner ear like a miniature piano, which is crazy. But the point is, I feel that we have a piece of work from Shih-Chii and piece of work also from Sevilla, because there is also a group from Sevilla that is working on the cochlea. I remember a colleague of mine, Daniel Gutierrez, that was working on the cochlea. And then we know that they can detect different frequencies, right? So bandpass filters, they can detect these frequencies, and then we have this cascade of events. But is there any application apart from detecting the different frequencies? Because I don't see, and I couldn't find any specific or clear real-world application using the neuromorphic cochlea data. Is it only me?
Yeah, probably only you. I'm just kidding. No, the cochlea modeling goes back a long way, right? Even if you put it in a context of neuromorphic cochlea modeling, it goes back to the early 90s, right? So Dick Lyon, who worked with Carver-Mead, did some of the earlier work on modeling cochlea. Then you had Lloyd Watts, who actually developed software that ended up in phones to do basically decomposition of speech as it's spoken, and then also to clean it up to make it more accessible to the listener, as well as doing source separation and a number of different things, different processing that was done on the signal itself. So in fact, I would argue that's one of the first neuromorphic, in quotes, in the new version of neuromorphic application in commercial space was actually the cochlea modeling and application. His company was called Ambient.
I just wanted to also put in a note for Chris Tumazu from Imperial College, who was producing silicon cochlea, not obviously quite in the same way. I mean, he's also considered part of the neuromorphic community. In fact, Ralph, didn't you almost work with Chris?
Yeah, I mean, I don't remember the exact details because it's been a while, but I know that Chris Tumazu was using subthreshold translinear circuits. These are, some of the techniques of circuit design that he was one of the developers of at the early points. This is, again, we're talking about the early 90s to develop examples of sound decomposition that was cochlea-like.
And my recollection is that these devices or descendants of these devices ended up both in phones also, as you say, but also in artificial cochlea for hearing aids for humans.
For hearing aids, exactly. So that's the other space where there's a lot of the early footprints of neuromorphic engineering. And then you move it a little bit forward and you get, I met Andre van Schaik, who has been one of the interviewees on this podcast, at the early version of the NeurIPS conference in Denver. And he was presenting a paper on cochlea modeling. That's what he was doing back then. So the early kind of silicon implementation of cochleas are actually from those groups, right? Chris Tumazu, from Dick Lyon, from Andre van Schaik, and another one person that we need to talk to as well at some point is Andreas Andreou. He was also doing this back in the day as well, right? And in fact, I would argue that one of the best models, in quotes here, obviously, of cochlea that was developed was Andre's one. And that's, I think, because he had a particular bipolar transistor that he had included in his circuit that made the matching between each segment of the cochlea, so the piano keys in the cochlea, to be as closely matched as possible. So the transfer functions were basically almost the same from one to the other. And I think that was also, and Shih-Chii can verify this, but I think that was also one of the reasons why Shih-Chii and Andre got together to do the work that they have done on the event-based cochlea, because he had, in silicon, one of the best cochleas out there. Now, as another application, Giulia, because you brought it up, is that around 2000, 2003, DARPA funded a project called the ASU, the Acoustic Sensory Unit, which was essentially a system for localizing sound from very, very far. So you're talking about just a tiny rumble of a truck at 5 kilometers. Can you basically predict the distance from you as well as predict the bearing? And Andre was one of the performers on this project with us. We did the closer range stuff. He did the farther range stuff. And again, he was able to demonstrate this cochlea models being used to do sound localization at this range, at the far range on very low, almost subsonic type signals, like in the 50 hertz range and so on, and it worked beautifully. So there's been quite a bit of application of the cochlea models over the years.
Yeah, and I don't know whether this would be specifically relevant to the cochlea model or not, but I have a good friend at Imperial, Julie McCann, who works on ubiquitous computing systems. And I would have thought that small, lightweight sound sensors that are sending out narrow bandwidth or low bandwidth signals that are just giving the information that you require, I would have thought that was just exactly what she needed for the kind of work that she does. And I know she's talking to neuromorphic people about neuromorphic sensors and processors in that kind of smart cities or ubiquitous computing space, smart dust, whatever you want to call it.
Very interesting. Yeah. The other thing that I would say as well is probably around the same 2000 to 2010 range, or maybe late 90s and up. You had a big push towards source localization, right? So multi-sources, multi-microphones. This is when ICA, independent component analysis, became really big. Bell and Shinovsky's famous paper on ICA came out around that same time. And one of the things that was being done was essentially trying to figure out what is the right number of recording nodes, right? That can be used in order to get the best source separation. And Gerd Kaumberg's, again, was one of the big players there and building these cochlea-like models into his chips. Gerd was always on this hardware side. So he built stuff, although he was still a theoretician as well. So that's why he's really cool. And then you've got the Bell and Shinovsky type approaches, which were purely computational. And they really work well together. And again, you keep seeing the cochlea models of the frequency decomposition stuff coming out and so on. And I don't want to raise Andreas' ire because he will say that there's a lot of stuff that happened in his lab, and I can't remember the name of the students at that time that made some really big contributions in that front. So cochlea modeling has been out there for a while, and it's good to see it now in the event-based space. That I would say is the newer segment of it.
Then I'm really happy that I asked because I learned a lot. I was too focused on the vision part, I think. So if I may, I'd like to bring attention also to the Delta network, which I found extremely interesting. And at the moment, I'm exploring some association of different sources of information, like, for example, tactile information with vision and tactile information with vision and proprioception. And when you have this association and this multiple sources of information, one of the problems is that the number of neurons explode. It's just impossible to understand and handle all of this. And I was very interested by this Delta network and how she can get rid of basically half of the neurons that were not activated throughout the processing. So I'm just thinking, like, what do you think, guys? Do you think that this could be a solution also for multiple sources of information that need to be combined and integrated with each other? What do you think?
So for me, it's not totally revolutionary, right? Because I think in the DVS, in the dynamic vision systems, that's exactly what we are doing, right? We have an image, we have places of the image where things are changing and other places they're not. And we only output the places that the changes are happening, right? And there is a comparison to a threshold. It tells you whether or not it's increased or decreased and so on. So now you're talking about an array, right, of pixels, and you're picking which signal you get outputted. In the cochlea sense, it's a linear array, again, with the different bands, and you're trying to figure out which one of the bands has information in it, right? So if I play a pure 1,000-tone signal to the cochlea, then only the ones at the 1,000 hertz will be outputting, and only if the signal that's in that 1,000 hertz bin has increased. If it hasn't, it outputs once and then that's it, right? So that's the way that I see it. I see it as an analog or mimic, if you will, of the DVS approach, but now applied to audio signals.
I think what Giulia was maybe getting at, though, is the Delta network is a network that's more generic, right? It's a processing network. It's not a sensor. And actually, I asked this same question to Toby Delbruck. He was also working on this same paper about this idea of introducing sparsity to what are essentially more conventional deep neural networks. And I think it falls into that category. So what she was saying about it is that she can reduce the amount of memory and the number of interconnects required to do the same task by using this Delta network protocol, algorithm, whatever you want to call it, which is interesting. Whether that would necessarily correspond to it taking what you were talking about, Giulia, which is multisensory input and making particularly good inferences from that I don't know. I think that's more of an architecture issue. My understanding, and Ralph, I'm sure you'll come in and correct me on this. My understanding is that in general, people who are looking at multisensory processing tend to process in sequence a little bit before they process in parallel. So they'll do a little bit of processing on the vision and the sound before they just throw everything together and try and make sense of that in a multisensory way. I could be wrong. That's my reading of the papers I've read in this area. So what I'm saying is I think that the Delta network is orthogonal. It's simply a way of taking a network that you've already got and making it more efficient with memory and interconnects than it would have been otherwise. That was my understanding.
Yeah, still, I think it might help maybe because of what we are doing at the moment is gain modulation, which actually is like taking inspiration from the cell in B6, I think. And it arises naturally, like just imagine that you have one array for the touch and one array representing the proprioception, and this basically associating when they are triggered. And then you associate in this basically layer of neurons, and then they are active only if you have these two association, right? Then I wonder if you can get rid of those that are not active, and that would be very cool.
I think my instinct is, having been in this field for a really long time and always had a little bit of magical thinking, I think, in the past about just throwing everything into a neural network and it'll sort it all out. I think as I've gotten more experienced, I've understood more that structure is really important, and that idea that you're processing different elements. So maybe you're not doing the full processing, or maybe some of it you're processing in one way, some is going off into a multisensory processor, but that structure is what's important. And then you'll have networks feeding into different networks and joining together. But as I say, I think what Shih-Chii was talking about was essentially a way of building a network, whatever the inputs and outputs are, that was just a bit more efficient than it would have been otherwise by using this technique. Ralph?
I think we need to maybe break it up into two pieces, right? So there is the delta modulation part that she talks about. And that to me is the more analogous to the dynamic vision system kind of scenario, right? Where you're looking for changes in the channels. And then there's the network construction, which is maybe that's where the data fusion, the sensory fusion from multiple different sources can be then combined and somehow co-processed to figure out whether or not there is coinciding information in order for it to keep, or non-coinciding information, or even orthogonal information to be thrown out. In the attention space, which is something that, Giulia, I know you are super interested in, there was a project as well with Ernst Niebuhr where I was just focused on the vision side, but Munya El-Hilali, who works on auditory attention, was looking at a combination of the two, right? How can you do visual attention and auditory attention and look for the intercept, right? Where, those two things happen at the same time. And that gives you a better sense of, I hear that bird tweeting in the bushes, and then I look and I see the bird, or it triggers my attention to that bush. And therefore, that becomes an important salient feature because there is also the sound overlapped upon it, right? So that sounds to me that would be that kind of fusion that you're talking about, Giulia. And of course, it doesn't have to be sound. It could be anything, right? It could be range. It could be other features of interest that you're looking for. One of the things that I want to also point out is, it's always, as the historian almost over here, I always want to point out some of the earlier work that takes advantage of neuromorphics and auditory signal processing and how mimics or overlaps with some of the works that Shih-Chii talked about. And word spotting is a classical example. And a person that actually, I think, does not get enough attention, if you will, in this field is the work of Paul Mueller, right? Because that was his driver. He was always interested in understanding speech, and he built some of the earliest neural networks, neural computers, specifically to do that. And you look at, what happened in the 70s, where he built it on the table, literally like the size of a table tennis, where he put 1,000 neurons together to detect speech. And then ultimately, when I was a grad student, we built it on chips, right? Oh, wow. So his work was to do word spotting, was to recognize different pieces of speech. And he had the cochlea layer, and then he had all the various on and off cells. Sounds familiar? Delta. Then he had all the feature extractors. So he was looking for different kinds of vowels and phonemes and things of that sort. And then ultimately looking for coincidences of these elements to say, oh, yep, that was that was a dog, that was a poodle, whatever he was basically detecting. So I think that's important to point out. And then also the fact that even back then, deep learning was being investigated. It just was not called that. And the network was too small for it to be anything. But multi-layers where you're doing backprop in between, yeah, they were being done. It's just that it was not called deep learning at the time.
And that's it for this week. Thanks, Ralph, for your insightful comments as usual, and Sunny for yet another interesting interview. In our next episode, Sunny will be talking to Dr. Amir Yousefzadeh, a neuromorphic chip designer who has just recently moved from IMEC to the University of Twente in the Netherlands. We hope you join us then.
That brings another episode of EE Times Current to a close. Thank you for listening, and thanks to our guest, Dr. Shih-Chii Liu. EE Times Current is available through all the major podcast platforms, but if you reach us at our website, eetimes.com, you'll find a transcript of this episode, along with other resources. EE Times Current is produced by EE Times. It was engineered by me, Taylor Marvin, at Coop Studios in Boulder, Colorado. The segment producer was Stephanie Munoz. Thanks for listening.